solve this dependent 3x3 system. Now at a glance, you wouldn't know that it's a dependent, very likely, but that doesn't matter. We'll start solving the system, and the fact that it's dependent will be revealed in just doing our normal process for solving the 3x3 system. So let's jump in and see how this works. Let's use the elimination method, so we can choose to eliminate either x, y, or z in any pair of equations. It looks like eliminating those x's wouldn't be too bad, so let's use equations 1 and 2. And I need to multiply one equation or the other by -1, so the coefficients will be exact opposites. I'll just multiply equation 1 by -1. So it would become -x minus 3y plus 2z equals -4. And equation 2 will remain x plus 7y minus 6z equals 12. When we add those two equations together, the x's are eliminated just like we wanted, and we get 4y minus 4z equals 8. Now, often we would just move on and grab a different pair of equations and eliminate the same variable, but I do notice that there's a common factor of 4 everywhere in this equation, so I'm just going to divide the equation, or both sides of the equation, by 4. So my equation would become y minus z equals 2. Now we have a linear combination of equations 1 and 2. Now let's grab a different pair of equations. Let's just grab 1 and 3. So if we're going to eliminate the same variable, I need to multiply equation 1 by -2. And in fact, let me write it this way so you can see it. I'm multiplying this equation by -2 so that we can eliminate the x's. So when we do that, equation 1 would become -2x minus 6y plus 4z equals -8. And equation, whoops, I wrote equation 2. We're using equation 3 this time. And that's 2x plus y plus z equals -2. And when we add these two equations together, again, the x's are eliminated, and we have -5y plus 5z equals -10. And again, I have an equation with a common factor of 5, and I don't particularly like a leading coefficient that's negative, so when I'm working with an equation like this, I often divide by -5. So my equation would become y minus z equals 2. Now remember, we now have two equations that are written with respect to y and z, and we put them together, and I have y minus z equals 2. Oh, and another equation that's identical. Y minus z equals 2, and here's where I recognize that something funny has happened. So I recognize that this system won't have just a single ordered triple for its solution. It will have an infinite number of solutions. And in fact, we just confirm that. Remember, we multiply one equation or the other by -1. I'm just going to do this officially. And when we get an equation where all the variables are gone and we have a statement like 0 equals 0, or it could even be 7 equals 7, or 13 equals 13, it means that the system has infinitely many solutions. And for some classes, that's fine to just represent the answer that way. But we can actually do better. We can actually say something about what those solutions look like. So we're going to introduce a parameter, and we'll call it t. We're going to come up with a representation of what the solutions look like. So I'm using the fact, I need a little more space here, so I'm going to use another piece of paper. I'm going to use the fact that y minus z equals 2 for every ordered triple that would be a solution to the original system. So if y minus z equals 2, and I'm going to let z equal t, my parameter is t, I'm going to substitute t into the equation right here, and I have y minus t equals 2, and I have y equals t plus 2. So I have a representation for z, and I have a representation for y. In fact, what I know is that a solution to this system would have this form: t for a z value and a y value that is 2 larger than that. I need to figure out what x is with respect to that same parameter. So we substitute t and t plus 2 into any of the equations you like. I'm just going to use equation number 1. So I have this: x plus 3 times t plus 2 minus 2 times t equals 4. And let me move that away so it's a little cleaner. And I have x plus 3t plus 6 minus 2t equals 4. Let me combine my like terms. And I'm solving for x. So I have x equals, I'm subtracting t, that's negative t. I'm subtracting 6, and that's minus 2. So now I have a representation of x with respect to t. So this ordered triple I know now is negative t minus 2, t plus 2, and t. And we have a general solution for this particular system right here. For this system, I know we have an infinite number of solutions, and they all have this form. Now, if you wanted some specific solutions, let's just find some. Let's find some ordered triples that would be solutions to this particular system. And I can let t equal any real number. So let's make it easy. Let's put t equals 0 into the ordered triple. So we have the opposite of 0 minus 2, that's negative 2. 0 plus 2 is 2, and 0. So negative 2 to 0 is an ordered triple that would work in this system. I could put in t equals 1 and find another solution. So I'd have the opposite of 1 minus 2, that's negative 3. I'd have 1 plus 2, that's positive 3, and t is 1. And you can substitute in and find as many solutions as you'd like. I could put t equals 100 in. And if you pop that in, you would have negative 102, positive 102, 100. And you could keep writing as long as you would like and find some very specific solutions to this system. Let's just confirm that in fact one of those works. Let's just use, we'll use the negative 2 to 0. So we're going to confirm that negative 2 to 0 is a solution to this system. That means we substitute that ordered triple into each equation. So we have negative 2 plus 3 times 2 minus 2 times 0. That should equal 4. That's negative 2 plus 6 should equal 4. That's negative 2 plus 6 equals 4. That works. Let's pop it into the next equation. Negative 2 plus 7 times 2 minus 6 times 0 should equal 12. That means we have negative 2 plus 14 minus 0 should equal 12. That's 12 equals 12. Let's pop it into the last equation. We have 2 times -2 plus 2 plus 0 equals -2. We have -4 plus 2 equals -2. That's -2 equals -2, and it checks. Similarly, each of these solutions that I wrote here would work in this particular system. Where'd the system go? There it is. Here's our general solution, and here are just three of an infinite number of possibilities for this particular system.